Hello, everyone, and welcome to another episode of Brick Programming. Today, we're actually going to be doing a challenge. I actually went and solved this equilibrium point. This is actually pretty straightforward, but it is an interview question that I believe I got when I interviewed with some company in Texas when I tried to apply there. But the question is, equilibrium position is in an array is a position at which the sum of elements before it is equal to the sum of elements after it. Given an array, ARR, your task is to determine at which point equilibrium first occurs in the array. If there's no equilibrium position, the answer should be -1. So they give us two examples, but basically, if we head on over to Paint, what we're getting is if we have an array, ARR equals, and I want to do 1, -1, 1, -1, and 1, is basically saying where is the first equilibrium point of this entire array? Is the equilibrium point here where all the things before this item add up to some number and all of these afterwards also add up to that number? So in this case, if I start at ARR sub 1, then therefore the left sum is 0. There's no items beforehand. And the right sum is -1 plus -1, 1. These cancel out and it equals 0. So the left equals the right. That is an equilibrium point. Now, how are we going to do this when we come to the code? Well, our code structure is this. We are only given an array as our input. So we have to determine everything afterward. So from here, let's say that we are given an array, and our array is 5, 4, 3, and 7. Let's make that one. Let's make that 2. And we need to figure out the equilibrium point. Well, first thing that we're going to need to do is we are going to need a left sum, right sum. We're going to need to know our index, and that's basically all the things that we need to know. Now, for this, we will need to do the following. One, loop through the array, and at each point, determine if it's equilibrium. And in order to do that, what we need to do is we need to sum up left point and right point, and then check equality of left and right sum. My handwriting is getting a little bit better, not too much. Of left and right. And then 3, if LSUM is equal to right sum, we return in else or -1. That's basically how our code is going to go. So with this, let's move on back to the code and start coding up something. So let's say, I just want to go through. So for int I equals 0, I less than length, I plus plus. Your first instinct is just make another method that will test the equilibrium, and you're going to pass in the array, and you're going to pass in I, which is the index. And then you're going to return what I is. Otherwise, you're going to return -1. This is your typical instinct that you're going to do. And therefore, you're going to make a Boolean test equilibrium of index of int array and an int of index. And you're going to say, okay, I have int sum1 and I have int sum2. And for all items, I equals 0, I less than index I plus plus. You're going to say that sum1 plus equals the array at I. And then you're also going to do for sum2, where you're going to say I equals index plus 1, I less than array.length, and I plus plus, and you can say sum2 plus equals array I. You're going to return sum1 equals sum2. Some things that we're forgetting here is we have to make sure that we initialize sum1 and sum2 to be 0. So therefore we know that these plus equals actually go into consideration. And I'm just going to run these samples and see, what we get. So I get 4 out of 10 tests passing, and so test 3, we get -1. The ones that we pass are the ones that we get -1. So if I look at 1, our output is 0, our expected output is 1, our output is 3, the expected is 4. So we're missing a +1 here to get the actual index. Since it seems from the example, since if we hand in one item, equilibrium point seems to be 1, which is from a count 1 perspective, but typically arrays in Java are a count 0 perspective. Start at 0 to indicate the index, or the start of the index. But the answer seems to be needing to be started at count 1. So we change that and we say, all right, cool, we passed all 10 examples. Let's submit it and see if we pass the other constraint of time. Time constraint is probably going to be your biggest one, and we don't manage to do that. And why is that? Well, what we're doing here is where we have an array that could go up to, I think that's either 10,000 or 100,000. And that's the big constraint. Really the -1,000 and 1,000 for the value that the index item is going to be, or the array index item is going to be, isn't really something that is constraining us. But this going up to 100,000 or 10,000 is really constraining us because we have 1 for loop, 2 for loops, and 3 for loops. And this 1 for loop is going to go through n, and these 2 for loops combined are basically doing n minus 1, which in total, since this for loop is calling these for loops, we basically have an n squared type of perspective here. We have n times n minus 1 kind of perspective here in the worst case scenario. So at that point, we would have a huge amount of time that's going into it. Now we're going to have to really, really bring this down. And what I'm seeing here, and I hope you guys see it too, is this for loop is counting up the same way that this for loop is counting. So we can theoretically get rid of sum1 and say just have one total sum in here. So that's what I'm going to do. So I'm going to say int sum1 is going to start here. And what I'm going to do, since sum1 is 0, and this needs to stay at index 0 because if it happens to be the first one, we might need to consider that being the equilibrium point. So I'm going to say, we'll add sum1, or we'll add the array I to sum1 after we pass through that section. Otherwise, I'd have to do an I minus 1 and have to do an if check, and that's going to add 1 time complexity to it every single time. It's going to add a instant time to it, but it still adds it over time. And if we're doing this for quite a lot, a million times, I've now added a million extra timestamps to this, and it's not going to be well doing. And I'm going to have to pass that sum1 also in method. So what I'm going to do is I'm now going to get rid of this. And what I'm going to say is once we hit an equilibrium point, that's basically saying that the sum previously must also equal the sum afterward. So therefore, this sum must equal 0 in the end. So what I can theoretically do in this point is just say, for the later half, I'm going to be taking away the entire time. You've given me a point in which it should be you've given me the high point. I now need to bring that down to 0 to hit an equilibrium. If that can equal 0, I know I'm at an equilibrium. Therefore, I'm going to do a minus equals for it. And I'm just going to check if sum is equal to 0. And this should be faster enough because instead of having to go through n and n again, so I get n squared, what I'm doing is I'm doing up to half on this, and then I'm doing the other half on this. Therefore, I'm only doing n on the iteration through the array. I'm not doing n squared, so I definitely already took the square root of my time on this. So instead of having 100,000 times 100,000, I now just have 100,000 as my time. And this should be a lot faster and should pass this time constraint. So if I submit it again, this should pass the time constraint. And would you look at that? We passed the time constraint and we still have the same end result of passing everything that we need to pass. So this is actually how you would find the equilibrium point. You would sum up all the items to the index that you're at currently. Then you would also sum up all the items after the index that you're at currently and basically set those equal to one another to check for equilibrium. This is actually a pretty simple thing to do. However, if you try doing what I did originally of passing you're going through the iterative process before, or you're going through it after you are indexing each item, you're basically doing an n squared operation, but if you're doing it as you're going along, you're doing an n operation time. So time is of the essence when it comes to programming, and that's why for most of these challenges, they always add that 3-second execution time constraint that you need to go through to make sure that, one, you're programming to the best of your ability and not just programming to get the answer, and two, making sure that your program actually runs efficiently and you're not doing something completely crazy. Because what I could also do here is I could do the same thing, but I can multi-thread. And if I start multi-threading, my time is probably going to jump exponentially, or my space is going to jump exponentially. So that's not something that we really want to do. So that is actually how we solved this problem. I hope you guys enjoyed. I hope you guys learned something. And you can definitely use this for any of your interviews. Just say that as I'm going along, I'm calculating how the sum prior to the index that we're at, and I'm passing that in to check the sum after where we're at. And I believe that this is the fastest way that you can go actually about it. So thank you all for watching. I will see you guys next time.